back to day one of probability. What did we do on day one? That was day two. What was day one?
Oh, the rock, paper, scissors?
Rock, paper, scissors. Now, what was the point in playing rock, paper, scissors? What were we trying to do?
See how many times you would get rock and paper and scissors.
But what was the point in that?
You see how much percentage you would get for each one.
If we could even what?
Even in like, see how many times we get more of for lesson?
What are we trying to match up?
How many?
Think. There's two words I'm looking for here. What two types of probability were we trying to match up? And it didn't work. Yeah, it was 1/3. We wanted to get 1/3, 1/3, 1/3. Where did that 1/3 come from? What's that called? What kind of probability is that? Is what we did. What's 1/3? For rock, paper, scissors. Starts with a T. You can look at your notes. Starts with a T. What was that one called? L. Look at your notes. I will give the whole thing away. Look at your notes. You have notes. Find them. What was the first type of probability we learned about? What? Theoretical. Theoretical is what we expect to happen, right? Now, that was where our 1/3 came from for rock, for paper, for scissors. When we actually played the game, what happened?
We got like way.
We didn't get 1/3, did we? We didn't get 33%. That's called what kind of probability when you actually do it? Experimental. So we were trying to get our theoretical probability and our experimental probability to match. But that didn't work. Why didn't they match? What did we find out? Why couldn't we get them to match? We didn't do it enough times. And then we watched the video of Bianca with coin toss, and she had to end up going to a football stadium to get 50-50, right? So then what did we do next on our experiment? What was the next experiment then? Dice. When we rolled the dice. And this time we got close to getting experimental and theoretical to match. Why?
Because
We did it a lot more times, 200 times, okay? That was our first couple of days. Theoretical is your plain old simple probability. And that was the first thing you did on IXL, which was C1. For example, if I have a 6-sided die, what is the probability of rolling a 1? 1 out of 6. What's the probability of rolling a 2? 1 out of 6. What's the probability of rolling a 3? 1 out of 6. What's the probability of rolling a 4? 1 out of 6. What's the probability of rolling a 5? 1 out of 6. What's the probability of rolling a 6? 1 out of 6. What's the probability of rolling a 7? 0. It can't happen. That's plain old simple probability. You understand that? Yes? Now, let's say that I'm going to do an experiment now, and I'm going to roll this die, and each time I roll one, I'm going to keep a count. So I want you on your paper to write these numbers down. 1, 2, 3, 4, 5, and 6. These are the numbers on the cube. And then we're going to keep up with the frequency. That's how many times I land on one of these numbers. Ready? So now we're going to actually perform an experiment. Right, here we go. What did I get the first time? A 1. So my frequency is a 1 at that one time. Okay, next roll. What I get? 4. Next. 2. Okay, next roll. 2 again. Next roll. 3. Next roll. I get a 3 again. Okay, next roll. I get a 5. Next roll, I get a 3. Next roll, I get a 2. And last, a 2. Okay, here's my question. What is the experimental probability of rolling a 5? That's not 1 out of 6. No, that's theoretical. That's theoretical. I'm talking about experimental of what I just did. What's the experimental for 5? 1 out of what? How'd you get 10? How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I rolled it 10 times. And I got a 5 1 time out of 10. That's experimental probability.
How many times you do the experiment?
Yes, it's your bottom number. Okay? What is the experimental probability of a 2? 4 out of 10. Good. What's the experimental probability of a 3? 3 out of 10. What's the experimental probability of a 6? 0 out of 10. It did not happen. Now, I'm going to make up some different numbers here. Let's say your chart looks like this. This is where it gets to be a little confusing. Now, the reason it's confusing is because now you have numbers on both sides. This goes to your ability to read a chart. These are the numbers on the cube. These numbers stand for what? How many times you landed on that number, correct? Okay, so using this new data, what is the experimental probability of rolling a 4? 4. 5 out of, that may not be 10. That's not 10 anymore. I gave you new numbers.
13.
20.
5 out of 20. Okay, good. What is the experimental probability of a 5, of landing on a 5? 7 out of 20. What's the experimental probability of landing on a 6? 2 out of 20. So do you see how you solve those? Okay, theoretical. Let's go back from day 1. What is the theoretical probability of rolling a 2? Theoretical. Teresa, what did you say? 1 out of 6. What's theoretical of rolling a 3? 1 out of 6. What's theoretical of rolling a 4? Experimental is when you actually have some data, where you've done something. Okay? Now, the next type of probability that we looked at after experimental and theoretical was compound. I want you to write that down. Was compound probability. What's compound probability when we have how many events? Two or more. Now, there are three key words to look for compound probability. Your three key words are the words and, write that down. The next word is then. And the last one's not a word, it's a grammatical commas. And, then, and commas. So here's the problem. We've got simple probability, which is where I say, what's the probability of rolling a 5? 1 out of 6. That's simple probability. Then we've got compound probability, where you have two events that take place. So then my question is, what's the probability of rolling a 5 and rolling a 2? I want two things to happen. I want a 5 and I want a 2. Okay? So what's the probability of rolling a 5? Huh? 1 out of 6. What's the probability of rolling a 2? What do I do with these two fractions? Multiply them. And that chance would be then 1 out of 36. I want two things to happen. What if I do this? What if I say, what's the probability of rolling a 4 and spinning the spinner and getting blue? Am I asking for two things? Yes, two events. Can I have 3 events? Can I have 4? Yeah, okay. Now, we've got simple probability. We've got compound, where we have two things to happen. Here's my question to you. If I say, what is the probability of rolling a 4 or a 5? A 4 or a 5. How would I solve that? Am I asking for both things to happen, or am I asking for either or to happen? Either or, one or the other, right? So I'm not doing compound, I'm not getting fraction, and multiplying. When I say 4 or 5, how many ways am I going to look on my dice? How many times can I get a 4 or 5 on here? How many times total? 2 times out of 6, which reduces to 1/3. That's still simple probability. It's not compound, okay? Because I'm asking for either or. Compound is when I say, what's the probability of getting a 5 and a 2? I want both to happen. Simple is when I want one thing to happen. All right. The next slide that we're looking at is where I want you to determine if it's compound or simple. Because when you take your probability test, there won't be things divided into sections. It will all be mixed up. So you have to determine whether or not it's simple, or if it's compound, or if we're drawing one of those big charts where we do sum of, that we did yesterday, or if you're using fundamental counting principle. Everything's going to be a mixture. So we're going to practice figuring that out. So let's look at number 1. I want you to number from 1 to 8 on your paper. Number from 1 to 8 on your paper. We're going to use S for simple and C for compound. Okay? Let's look at the first situation. The probability of 3 or 5. Is that simple or is that compound? That's simple. Why is it simple? It's not using the key words, but furthermore, why is it simple? Am I asking for two things to happen? Or am I asking for either or? So that means either I want this to happen or either I want this to happen. I don't want two things to happen. It's kind of like me saying either I'm going to sit down or I'm going to stand up. I'm going to choose one or the other. I'm going to stand up and teach. I'm not going to sit down. I'm not doing two things. I'm doing one thing. Either or. So don't let that confuse you. So this one is simple. So we're going to put an S for simple. Number 2, the probability of getting an odd number. Simple or compound? Simple. Good. Number 3, the probability of getting a 7 and a 2. That's compound because I want two things to happen. Number 4, the probability of not 6. Simple. Number 5, the probability of blue and green. Compound. Number 6, the probability of blue or green. Do I want one thing or two things? One thing, so that's going to be simple. Number 7, the probability of blue, comma, green. Compound. Number 8, the probability of 8. Simple. Okay. Now that we can identify, let's actually solve some. Number from 1 to 12. Okay, now we are using our spinner here. Let me bring this to your attention. When you see one spinner, you're probably thinking these are all going to be simple. Because compound, you've kind of been trained to look for two things to take place, right? A die and a spinner. That's what you're thinking for compound. That's not necessarily true. I can spin this spinner more than once, can I? Can I go one, like, look, right here, I have a spinner. Can I go one spin, another spin, and another spin, and another spin, and another spin? That would be compound. So I can use one spinner and keep spinning it multiple times. Yes? Okay. So just because there's one piece of one tool up here doesn't mean it's automatically all going to be simple. You got to be careful with that. All right, number 1. What is the probability of spinning this spinner and getting green? Huh? 3 out of what? 8. Good. 3 out of 8. Okay, number 2. What is the probability of blue? 1 out of 8. Number 3. What is the probability of red or yellow? 3 out of 8. Why is it 3? That's right. I got to count all of these, right? I'm looking for that steering to land on either one of these 3 spaces. That would be 3 out of 8. Number 4, the probability of red and yellow. Do I want one thing to happen or two things to happen? Two things. This is compound. So what do? Nope. Red and yellow. No, this is compound. I'm wanting two things to happen. When we have compound, what do you have to do? Multiply. Fraction times fraction. It's not the same as red or yellow. I want two things to happen. And when you want two things to happen, you have to have fraction of the first times fraction of the second thing. That's compound. Okay, what is the fraction for red? 2 out of 8. There's a 2 out of 8 chance I can get red. What's the fraction for yellow? 1 out of 8. And what do I get? 2 over, that's not 16, 64. Now, can I reduce that?
Yes.
What do I get? 1 over 32. A 1 out of 32 chance. It's not really going to happen. You got to remember, simple, compound. Compound, fraction times fraction. Number 5, not white. 7 out of 8. Number 6, blue, comma, green.
You're comparing two things. So
One
it's gonna be
time, 1
compound.
over 8 times
1 over 8 times
3 over 8.
3 over 8, which will be
3 out of 64.
3 out of 64. Good. Number 7, red or green.
5 over 8.
5 over 8. Excellent. Number 8, red and green.
2 over 8 times
2 over 8 times
3 over 8.
3 over 8, which gives us 64, which can be reduced by 2. And we get 3 over 32. Okay, number 9, red, comma, green.
2 over 8.
Times? It's the same thing. Good, Tanya. Same thing. So 3 over 32 again. Okay, next, number 10, probability of a color. 8 out of 8, which is equal to 1 whole, which is 100% chance of happening. 11, the probability of purple. So just be 0. 12, let's see if I can trick you on this. The probability of blue 3 times in a row. Blue 3 times in a row. It's going to be what, Amy? It is compound. Yes, ma'am. It's compound. You got it. Because how many times am I doing it? 3 times. So how many fractions should I have? 3 fractions. And what are those fractions? 1 out of 8 times 1 out of 8 times 1 out of 8. Yes, ma'am. The thought process that Amy went through was perfect. And then Tanya and Osvaldo caught up with it. She said it's compound. That was first. Compound means I got to multiply. Then I said, how many times am I performing it? 3 times. That means 3 fractions. Okay? 1 times 1 times 1 is 1. 8 times 8 times 8 is what? 512. Good. Next slide. Number from 1 to 10. Okay. What do you think these questions are going to be?
Compound.
Why? What else do you notice?
2 symbols.
Two tools, right? We got a die and a spinner. All right, here we go. Number 1, the probability of 3 and red. What's my first fraction?
1 out of 6.
1 out of 6, yes. Times
3 out of 8.
3 out of 8. That equals 3 out of
48.
Can I reduce that? Yes, by 3. That gives me 1 over 16. Okay, you're going to do 2 through 10 on your own without me. Okay, so pause. 2 through 10, go. Okay, let's start with number 2. The probability of 5 and blue. What's the probability of 5? What's the probability of rolling a 5? 1 out of 6. And blue? 2 out of 8, which gives us 2 out of 48, which is 1 over 24. Okay, number 3, the probability of 4. 1 out of 6 times 1 out of 8, which is 1 out of 48. Number 4, the probability of even. 3 out of 6. White,
One out of 8.
which is 3 out of 48, which reduces to 1/16. Number 5, the probability of prime. 3 out of 6 times red. 3 out of 8, which is 9 out of 48, which can be reduced by 3, which is 3/16. Okay, number 6, the probability of odd. 3 out of 6, and not green, which gives us 21/48, which can be reduced by 3, 7/16. Number 7, the probability of 7. 0. So are we done? We can't get both, can we? That's a done deal. Number 8, the probability of a number smaller than 5. 4 out of 6, and red is 3 out of 8, and we get 12 out of 48, which is 1/4. What percent is 1/4? 25%. Excellent. Okay, number 8, the probability of a number greater than 1. Greater than 1.
5 out of 6.
5 out of 6, and not red. 5 out of 8, which is 25/48. Number 10, a number and a color. It's going to be one whole, right? Because you get 6 out of 6 times 8 out of 8, which will be 48 out of 48. What percent would that be? 100%. Okay, next slide. After that, after compound, we learned fundamental counting principle, and we learned tree diagrams. Remember the tree diagram over plain bagel, raisin bagel, sports drink, water.
Combination.
Yeah, the combinations. Then we learned the one over you getting dressed for school in the morning. My gosh, y'all should think about a Nike shoe. If you go to Nike ID, they have a website, and you can design your own Nike shoe.
Yeah, my nephew did that.
Yeah, but if I had you to draw a tree diagram for a Nike shoe, you would hate me. Because on a Nike, you can choose the color of the tongue, the laces, the swoosh. The tongue is that part of your shoe. You can decide the color of your sole. If you want text, you have all these options. So let's just say they have 50 colors for swooshes. Let me show you what I'm talking about. Hold on. Okay, I can't find the website, but there is a website that allows I can get to MathWise that allows you to customize a pair of Nikes, and it shows all the different choices. Like there's like 100 colors, so that would be 100 times. There's 500 colors for the actual little Nike symbol. So you do 100 times 500 times the color for the soles. There would be a lot of big numbers to multiply to customize a Nike shoe. If you had to draw a tree diagram of that, that would be unreal. You just couldn't. Okay? So, thank goodness someone came up with fundamental counting. Now, if we look at this situation, we have Elmer. He went to an ice cream shop that served 3 flavors: vanilla, chocolate, strawberry, 2 kinds of cones, waffle, cocoa, and 3 kinds of toppings: M&M's, Oreos, sprinkles. How many different combinations of one flavor, one cone, one topping can Elmer get? Draw a tree diagram to illustrate his choices. So we're going to start our tree diagram with vanilla, chocolate, strawberry. So I'm going to use V, C, and S. So if I order vanilla, I can put it with what kind of cone? Waffle or a cocoa. Let's say I get vanilla waffle cone. Now what kind of topping? M&M, or I could get Oreo, or I could get sprinkles. Okay. The next cone that I could order, I could do vanilla cocoa cone with what toppings? M&M, or Oreo or sprinkles. Okay, that's the first one. How many combinations so far? 1, 2, 3, 4, 5, 6 so far just from vanilla. Okay, now let's do chocolate. We can do chocolate, we can do waffle or cocoa. I'm about to bring chocolate over here so I have room. And then we could have M&M. So you're doing this on your paper. You're doing this on your paper. M&M, Oreo, sprinkles. Or I could have chocolate cocoa cone, M&M, Oreo, sprinkles. That gives us 6 again, right? And last is strawberry. I could have a waffle or a cocoa cone, M&M, Oreo, sprinkles. Or a cocoa cone, M&M, Oreo, sprinkles. And that's 6 again. Okay, now let's do fundamental counting principle. We have 3 times 2. So there were 3 flavors times 2 cones times 3 toppings. What's 3 times 2? 6 times 3 is, so we got the same number. We got 18 both times. 18 from fundamental counting principle, or you can get 18 by counting the outside branches of your tree diagram. A lot easier. Yeah, this can be long and frustrating. Okay? All right. Are we good? All right. Okay, right here you can see the Nike site that has all the outcomes for a Nike shoe. So if we build a tree diagram of this site, you would have to list yellow, purple, burgundy, pink, light purple, dark blue, medium blue, very light blue, sea green, lime green, yellow, white, gray, olive, and charcoal as your first part of your tree diagram. And then you'd have to do yellow to yellow, yellow to burgundy, yellow to light purple, yellow to dark purple, yellow to navy blue, yellow to this blue, yellow to that blue. So your tree diagram will get really big, and that's just 2 parts of the shoe. This video shows you what that looks like, kind of. So let's take a look at it. So that's yellow, orange with all the choices, burgundy with all the choices, pink with all the choices, purple all the choices, dark purple choices, dark blue, blue, light blue choices, green, lime green with all the choices, yellow all the choices, white, gray, olive, and dark gray with all the choices. That would be a huge tree diagram. So if we didn't have fundamental counting principle, that would be huge. And that's just 2 of the choices. Now we can look at the actual swoosh. So that would be another part of your tree diagram. So you'd have to also incorporate those colors for every single branch on the first tree diagram that you drew. Then you've got the lace. That will be another part of your tree diagram. So your tree diagram would get very, very, very big if you were just looking at a Nike shoe. Then you've got your midsole. That can change. And then you've got your midsole rim. That can change as well. So the branches just keep getting so big, there's no way. Then you've got your tongue top ID that can change. So it's a blessing that we have fundamental counting principle, because if not, it would be really hard to draw a tree diagram of all the different ways that you can make a Nike shoe. And you can see here, this is how many combinations. That's how many things you would have to make on your tree diagram. So fundamental counting principles right here, 16 times 13 times 16 times 19 times 7 times 18 times 13. 103,574,016 Nike shoe combinations. Imagine drawing that in a tree diagram if we didn't have fundamental counting principle.